All right, now let's talk about a circulatory structure and function in our next group, the non-bird amphibians and reptiles. Before I dive into this topic, I want you to take a minute to review some concepts we've covered already in lecture, which is to think about how amphibians and non-bird reptiles breathe, okay? And this is just very generally speaking, remembering that there are some distinctions between how amphibians breathe and how the non-bird reptiles breathe. So take a minute, jot down some notes, see what you can remember about breathing function in the amphibians and non-bird reptiles. Okay, so now that you've been thinking about how these groups of animals breathe, let's take a look at how their circulatory architecture differs from what we've seen for the other animal groups we've examined so far. So up top on the right-hand side of this slide, I've got an image from your textbook that illustrates the architecture for the amphibians. And then the other image pictured here is circulatory architecture for non-bird reptiles, so turtles, lizards, and snakes. As we start to study these diagrams, first thing I want you to notice is both of these groups of animals now have separate atria, right? So there's in the amphibians, notice that the left and right heart, the organization's a little bit strange here. We'll deal with that. But here's our two atria in the amphibians, and then here are our two atria in the turtles, lizards, and snakes. So more simply put, these groups have what we'd refer to as three-chambered hearts instead of two-chambered hearts or four-chambered hearts that we've already seen. Okay, so in the ventricle, these animals have an incomplete septum. So there may be some tissue present, there might be no tissue present, but it's not a completely separated out ventricle. And even though the septum in the ventricle is not complete, there's still limited mixing of blood across the left and right side of the ventricle. So in these circuitry diagrams, right, that's illustrated with these little stripes coming across between the halves of the ventricle, just to illustrate that more oxygenated blood in the left side of the amphibian heart is going to remain primarily on the left side of the ventricle, that single ventricle, before traveling out to the systemic tissues. And the relatively deoxygenated blood on the right side of the amphibian heart will remain on the right side, and that blood will largely get directed towards gas exchange organs, remembering that in amphibians there's gas exchange that will take place both in the lungs for adult amphibians and then also across the skin, okay? So along with that, certain subgroups of reptiles have some extra exotic elements to this whole organization. Specifically, as I've highlighted here, pythons and the varanid lizards have discrete pressures on either side of their ventricle. So if we think back to what we talked about with mammals and birds, with the right side of the ventricle feeding the pulmonary system, right, we need to send lower pressure blood through the pulmonary system to avoid pulmonary edema. The same is going to be true for these reptilian groups, right? If they're sending blood to the lungs, there's a risk of edema if that blood is too pressurized. So the ventricle will not squeeze evenly across the two sides of the heart, and that will help to facilitate lower pulmonary pressure in those guys. So there's one more thing we want to talk about with amphibian and non-bird reptile breathing, which is you might remember that both of these taxonomic groups engage in different forms of intermittent breathing. So they're not breathing consistently in and out all the time. They can go through periods where they will hold their breath. So with intermittent breathing, there's something very convenient about this type of circulatory organization for an animal that is an intermittent breather. And that is that if your blood is not stuck always traveling through your lungs, then when you're in a situation where you can't really breathe, and if you think back to the lungfish, this is kind of similar to the lungfish situation, you don't necessarily have to put a lot of energy to send blood through your lungs when that's really not going to be all that beneficial. If the septum is incomplete, then under certain circumstances, that could mean you could experience vasoconstriction on the pulmonary circuit. If there's more vasodilation on the systemic circuit, then instead of uselessly passing blood through the lungs, you can divert most of the blood towards the systemic circuit and just continue circulating it there. Okay, so that can be really helpful for animals that dive because they can save the energy that might be used to pump blood across the lungs for other functions. And those animals will also make other adjustments to peripheral vascular resistance, right? Using combinations of vasodilation and vasoconstriction to facilitate and redirect blood flow under different circumstances. So here's a redrawn version of these circuitry diagrams, and I've switched these to make them match more directly with the other circuitry diagrams we've seen. So I've got the left heart on the bottom, the right heart on the top. The main ideas are still very much the same as from the diagrams provided by your textbook. Focus on the fact that there are two different atria, there's partial mixing in the ventricle, and we're starting to see a separation of deoxygenated blood flowing back across the gas transport organs, and oxygenated blood then flowing across the systemic tissues. And this right-hand diagram for the reptiles, I just want to also add the note that in general we don't see gas exchange across the skin of reptiles. We only see that in a handful of turtles. So for the most part, you can just erase this from this non-bird reptile diagram and just picture the remaining of the circuitry here. That's not the end of this story. We also need to talk about the crocodilians, and that's because the crocodilians are especially cool. So crocodilians have divided hearts. So we now see a left heart and a right heart. So I've pictured that over here, okay? And again, I just think the way your book has laid that out, it's a little bit confusing. So here's our left heart, here's our right heart, okay? And so we see a complete separation between those. However, we see a connection point downstream in the circulatory system. So rather than the potential for mixing in the ventricle, crocodilians have two aortas, okay? So here's a picture from the book that illustrates, so left ventricle, right ventricle. There's a cog valve to the right ventricle, and we'll take a look at what that accomplishes in a moment. And then there are flap valves here for both the left and right ventricles, okay? So if we scrutinize this, when a crocodilian is breathing air, the cog valve in the right ventricle will be open. So I'm going to jump over to the diagram on the right side of the slide. So when breathing air, this cog valve will be relaxed and open. So deoxygenated blood flowing back from the systemic tissues through the right heart. Pressure forces will favor movement of that blood across the lungs, reoxygenation, traveling through the left heart, and back out to the systemic tissues, okay? Now, when this crocodile is diving, this cog valve will close or become more restricted. So under those circumstances, pressure forces will favor use of the other branch of the aorta from the right heart to circulate back through these systemic tissues. So basically, when a crocodile is diving, it too can bypass the lungs and just redivert blood flow through the rest of its tissues when it's experiencing apnea. So think that is pretty amazing as far as circulatory organization goes. And hopefully, having seen these things in the amphibians and non-bird reptiles, you can start to imagine how we got to the full four-chambered hearts that we see in the birds and in the mammals. So up next, we'll take a look at the invertebrates that have closed circulatory systems.